In this video, we will be talking about sets and their basic operations. A set is a collection of objects which we will call elements or members. One way to describe a set is using roster notation. With roster notation, we list the elements of the set. For example, suppose I wanted to list a 4-element set that had the elements 1, 2, 3, and dog. Then I could list the set as follows. With roster notation, you begin with an open curly brace, then you list your elements separated by a comma. 1, 2, 3, dog. And then you end your set with a closed curly brace. In general, we're going to want to be able to reference this set, so we can give it a name. For example, we could call this set the set A. We'd like to be able to describe if something is in the set, and we have a special symbol for that. It's element of. For example, 1 is an element of the set A. We can also strike through this symbol to say that something is not an element of the set. For example, cat is not an element of A. We would like to talk about the cardinal number of a set, which is the number of unique elements in the set. And the symbol we use to ask that question is n of A. In our example, A had 4 elements, so n of A would be 4. There are two special sets that have special symbols that we use for them. One is the universal set, and we use a capital U to denote the universal set. More will be discussed about this later when we talk about complements of a set. Another set that has a special symbol is the empty set. And the empty set is defined as the set that contains no elements. A common mistake that people make is to say that this is the same as the set containing the number 0, but 0 is an element, so this is not the empty set. Another misuse of this notation is to say that it is a set containing the empty set, but this is not the same set as an empty set. Sets can be compared, so let's look at a comparison of two sets, and the first comparison we're going to look at is equality. In doing this, let's look at a new mathematical symbol that you may have seen, but you most likely have not seen in the past. It's an upside down capital A. This is read for all or for every. And when we use this symbol, we're saying that what we're about to say or what we are talking about is true in all cases, for every case. So let's go ahead and define set equality. The textbook defines it in words. We'll define it using math symbols. You can compare what we use here to what's in the textbook. They both mean the same thing, just to get an idea of different ways to write things down mathematically. So the definition of two sets being equal is as follows. A equals B if for all little a in capital A, little a is in capital B, and for all little b in capital B, little b is in capital A. So let's talk about what this says. In the beginning it says for all little a in capital A. Little a is a variable, and it's standing for every element in capital A. And what we're saying is for every one of those elements in capital A, that element can be found in capital B. So any object in the set A is found in the set B. The second part says it also has to be true that every object in the set B can be found in the set A. Basically, all this says is the two sets contain the same collection of elements. So let's take a look at some sets and decide whether or not they are equal based on this definition. So here we have 3 sets. Set A is the set containing the elements 1, 2, 3. Set B is the set containing the elements 2, 1, 3, 2. Set C is the set containing the elements 1, 3, 2, 5. So let's decide if any of these sets are equal. Let's begin by looking at sets A and B. So our definition says that these two sets are equal if for all A in A, that A can be found in B. So let's start with all of the elements in A. A contains the element 1. So we look in the set B and we ask ourselves, does it contain the element 1? And the answer is yes, it does. Then we look at the next element, the element 2. And we look inside set B and ask ourselves, does the set B contain the element 2? Yes, it does. Then we look at the last element in set A, 3. And we look in set B and ask ourselves, does it contain the element 3? Yes, it does. So the first part of the definition holds. Let's look at the second part of the definition. It says that every element in set B must be found in set A. So we do the same thing. We start with the element 2. Can we find that in set A? Yes. We go to the element 1. Is that in set A? Yes. 3. Is that in set A? Yes. 2. Is that in set A? Yes, it is. So actually, it turns out that the sets A and B are equal. This actually gives us some information about how sets are defined. For one thing, there's no concept of repetition of elements. So while sets A and sets B are equal, set B really is a set that we would never write down because we never write the same element twice. There's no reason to, because having the element 2 listed in the set B twice doesn't mean anything. The set B still only contains the elements 1, 2, and 3. In fact, if we asked for the number of elements in B, the answer would be 3, because the only elements in B are the elements 1, 2, and 3. So there's no concept of repetition. An element is either in the set or it's not in the set. The other thing you'll notice is the elements were not in the same order. Sets have no ordering. So if a set contains the elements 1, 2, and 3, there is no order in which they are listed in the set that's important. I could have listed them as 1, 2, 3, 2, 1, 3, 3, 1, 2, etc. It doesn't matter. Now let's see if A is equal to C. Now we already know that A is equal to B, so if A is equal to C, then B is also equal to C. So we test the definition of equality. A contains the element 1. Yes, that is in the set C. A contains the element 2, which is in the set C, 3, which is also in the set C. Now we compare C to A. C contains the element 1, which is in the set A, 3, which is in the set A, 2, which is in the set A, and 5 cannot be found in the set A. Therefore, A does not equal C. And likewise, B does not equal C, since we know that A is the same as B. Consider numbers. When you compare two numbers, one of the things you can do is decide whether or not the two numbers are equal or not equal. Another comparison you can make is one number less than or equal to the other number? And with sets we have a concept that's similar to that, and this is called the subset. And the symbol for the subset looks similar to a less than or equals, but it's a little different. So let's go ahead and define a subset. B is a subset of A. Now notice it looks like a less than or equal to, but the top portion does not have a sharp point. It's more curved. So B is a subset of A if, for all B in B, that B is in A. And that's it. Looks like part of our definition of equality. Basically, all we require is that everything you can find in B, you can find in A. And that's the only thing that's necessary for B to be a subset of A. So let's look at some examples of sets and talk about whether or not one is a subset of the other. So here are three sets. A is the set containing 1 and 2, B is a set containing 2 and 1, C is a set containing 2. And let's start with the question, is A a subset of B? For that to be true, every element in A must be found in B. Well, 1 is found in B and 2 is found in B. So all the elements of A can be found in B. Therefore, A is a subset of B. Well, is B a subset of A? And if you look, it is. Every element in B can be found in A. Well, let's look. Is A a subset of C? If A is a subset of C, then every element in A can be found in C. But notice that A has the element 1, which I cannot find in C. So A is not a subset of C. Likewise, you can test B B is not a subset of C. Now we can test C. Is C a subset of A? Well, C contains the element 2, which can be found in A, so C is a subset of A. And let's check C with B. Every element in C can be found in B, so C is a subset of B. Now let's suppose that we add an extra set here, just for comparison purposes. Suppose we had a set D that contained the element 3. And the question is D a subset of A? Is D a subset of A? Well, D contains the element 3, and 3 is not found in A. So D is not a subset of A. Likewise, the things in A cannot be found in D, so A is not a subset of D. So unlike the less than or equal to symbol, sometimes if you have two sets, they're not comparable. Neither one is a subset of the other. Now we're going to talk about strict subsets. We're going to learn another new math notation, and that is the capital and backwards E. So backwards capital E, and that is there is or there exists. So remember, the upside down capital A is for all. Now a strict subset is like a strict inequality, so let's look at the definition of a strict subset. A set B is a strict subset of a set A if for all little b in capital B, little b is an element of A, and here's where we use that there exists a little a in the set A such that the little a is not in the set B. So let's look at the difference between for all and there exists. For all says it has to be true in all cases. So when we say for all little b in B, little b is in A, we mean every element in B must be found in A. The second piece says there exists. All that means is we need one example. There can be more, but we just need one example. So we need one example of an element in A that cannot be found in B. So let's look at our previous examples of sets A, B, and C and decide if any of these are strict subsets. For example, is A a strict subset of B? Well, for that to be true, for A to be a strict subset of B, every element in A must be found in B. That's true. And there must be something in B which cannot be found in A. But that's not true. There's nothing in B that cannot be found in A. So A is not a strict subset of B. Likewise, you can test and see that B is not a strict subset of A. What about C? Is A a strict subset of C? No, it's not. It's not even a subset. But is C a strict subset of A? And the answer is yes. And let's look at why. Every element in C can be found in A. C contains the element 2, and 2 can be found in the set A. And A contains something which cannot be found in C. It's the element 1. 1 cannot be found in C. Therefore, C is a strict subset of A. Likewise, C is a strict subset of B. There's an example in your textbook which has 3 sets, E, F, and G, and it compares these 3 sets using all of the symbols we've learned. Subset, strict subset, equals, not a subset, not a strict subset. So that's a good example to look at this point, to get a better idea or a firmer grasp on this concept. Before we can continue talking about set operations, we need to discuss another method of describing a set, and that's set builder notation. Set builder notation is actually the more commonly used set notation. So let's look at how this works. So just like with roster notation, you can give your set a name. You start set builder notation with the same curly braces. Now what you do is you describe a generic element of the set, like a variable, so x. Then you have a vertical line which is read such that, And this vertical line indicates to the reader that everything after this vertical line is going to define the elements x of the set. And then to define the elements x of the set, you can use any combination of methods you would like, for example, words or math symbols. I could say that x is greater than 0, x is less than or equal to 100, x is an integer. I've just defined the set A to be the set of all integers that are greater than 0, so starting with 1, and are less than or equal to 100, so ending with 100. Notice this is a lot more convenient than listing out the numbers 1 through 100. Another thing we'd like to look at before we start defining some more set operations is a Venn diagram. A Venn diagram is a graphical representation of a set. For example, suppose I have a set A which contains the elements 1, 2, and 3, and here's where we're also going to talk about universal sets. Suppose I have a universal set that contains the elements 1, 2, 3, and 4. Now a universal set must contain all of the elements of any set you're discussing in reference to that universal set, but it may also contain some additional elements. Another way to say that is every set is a subset of the universal set. Now a Venn diagram is a graphical representation of this information. So we use a box to represent the universal set. We'll label that U for universal set. And then we can have a circle, or any other shape really, that we'll label A for the set A. And then inside these sets, we list all of the elements. So for example, the box contains the elements 1, 2, 3, and 4. All of those are inside the box. The set A contains the elements 1, 2, and 3. All of those elements are in the set A. Notice that the concept of subset and strict subset are very obvious using a Venn diagram. A is a subset of U because it's contained inside U. The entire circle is inside the box. It's a strict subset of U because there are elements that are not inside A, even though A is contained in the set U. We'll look at some more examples of Venn diagrams as we describe some set operations. The first set operation we're going to talk about is the intersection. If we have two sets and we find their intersection, we write it as follows: A intersect B. And the intersection of two sets is defined as the set of all things x such that x is in A and x is in B. So it's the set of all things they share in common. It's the set of all things x such that x is in A and x is in B. If we look at an example, A equals 1, the set containing 1, 2, and 3, and B is the set containing 2, 4, and 6. Then A intersect B is a set, and it is the set of all things that are both in A and in B. So the set of all things that they share in common. The only element they share in common is the element 2. A graphical representation of the intersection of two sets. I have a set A and I have a set B. Graphical representation of the intersection of two sets is the region they share in common. So this is a generic graph. This works for any sets A and B. Notice I haven't actually listed any elements in this diagram. The region that they share in common, the place that they overlap, is their intersection. Next, we'll look at the union. The union of two sets is written as follows: A union B. Now notice that U looks exactly the same as the U for the universal set. It's not actually a U, it's a union symbol, written properly, and if you look in the textbook, it's a little broader than a U. But when you're handwriting it, it looks just like a U. But there's no confusion here because we would never write AUB if U was a set, so that must be the union symbol. A union B is a set. It is the set of all things x such that x is in A or x is in B. Now notice the difference between the intersection and the union is the difference between and or. Oftentimes people read the intersection as and, A and B, and the union is or, A or B. When we say that X is in A or X is in B, we mean that an element X is listed in the union if it can be found in either set, the set A or the set B, or both for that matter. So, using our A and B listed above, A union B would be any element found in either set. Well, I can find a 1 in there, a 2, a 3, a 4, a 6. All of these elements can be found in either A or B. And a graphical representation of the union, using a Venn diagram, we have our set A, we have our set B, and a graphical representation is anything contained in one set or the other so that is a graphical representation of the union. The last operation on sets that we'll be looking at is the set complement. If we have a set A complement, so that small little symbol is the complement, is the set of all things X, such that X is not in A. So it's the things that are not in A, and X is an element of the universal set. So we must have a universal set if we're going to describe complements. So let's suppose we still have the same set A from above. A is 1, 2, 3, the set containing those elements. And let's suppose that our universal set is the set containing 1, 2, 3, 4, 5, and 6. Then in this example, a complement is the set containing, so I need to find the elements of the universal set which are not in A. 4, 5, 6. Graphical representation, using a Venn diagram of a complement. This is my set A, and the complement is everything, all elements, found outside of A. Notice that even if I had a set B here, that does not change the complement. The complement is some of the elements in B, but not all of the elements in B if B overlaps with A. Let's look at an example of combining some of these concepts by finding a Venn diagram description of A intersect B complement, as well as the set A intersect B complement given three sets, A, B, and the universal set. So let's suppose A contains the elements 1 and 2, B contains the elements 2 and 3, and U contains the elements 1, 2, 3, 4. And we would like to find A intersect B complement. So first of all, we should find B complement. B complement is the set of all things not found in B, but that can be found in the universal set. That's 1 and 4. So now A intersect B complement is the set of all things that they share in common. It's the things that are in A and in B. The only thing they share in common in this example is the element 1. So A intersect B complement is 1. Now let's look at a generic Venn diagram graph of A intersect B complement for two sets, A and B. So we have our universal set, we have our set A, we have our set B. We would like to find A intersect B complement. Now one way to do this is to, if you have multiple colored pens, shade the sets A and the set B complement with different color shadings. So let me begin by doing that. First I'm going to shade A with blue. Here's my set A. Then I'm going to go ahead and I'm going to shade the set B complement with green. Now if you don't have different color pens, you can use different styles of shading. For example, now I'm using just horizontal lines for B complement, all the things outside of B. And then finally, your final answer, in this example, I want to find the intersection of A and the set B complement. Those are the parts that they share in common. So with two different types of shading, I'm looking for the region that is shaded by both types of shading. And in this example, it is this region. Now, even if you have multiple color pens, it's a good idea to do your work on one diagram and then list your answer on another so that there's no confusion about what region is shaded. So in this example, A intersect B complement is given by that region. The last thing we're going to talk about are De Morgan's laws. Given any two finite sets, A and B, A union B complement. So the complement of the union is equal to the intersection of the complements. So complements will distribute through parentheses, but they change unions to intersections. And the complement of an intersection, so if we take the intersection of A and B and find its complement, is the union of the complements. And these two properties can be proven using Venn diagrams. Draw the Venn diagram for the complement of A union B, then separately draw the Venn diagram for A complement intersect B complement. You will find that they're the same Venn diagram, so these are the same sets. Likewise, find the Venn diagram for the complement of A intersect B, and compare that to the Venn diagram for the complement of A union with the complement of B, and you will find that those two are the same Venn diagrams, and hence these are the same sets.